Okay, so as I mentioned, this filter, okay, is so-called pre-weighed operator, okay? So when you apply the software for edge detection, sometimes you need to know what does it mean, because it just used the original author that developed this filter, okay, called pre-weighed, okay, the author's name 啊，这个是难名。可是我们这个领域大家都习惯这样用的，没有人会说叫不出名字，所以你要知道 ，okay, whenever you select pre-weight, it means okay all the element is 1 or minus 1, okay, pre-weight operator. But anyway, you need GX and GY, okay? Unless you care only about vertical line, then you apply this GX only. But most of the case, we will care both. So you need to calculate GX and GY, okay, at the same time. Okay, and as I mentioned, the extension is so-called Sobel operator, the most famous one, okay? Even for 3x3, what could be the direction? What could be the direction for a 3x3? What will be the resolution of the direction? For this 3x3, there's only 8 directions, right? So what will be the resolution? 45 degrees, 45. But in a very high contrast image, in an ideal situation, okay, there's a paper talk about the Sobel operator if only if you have a very high contrast, just very close to binary image. I mean, the resolution can be as good as 5 degrees. Even you use only a 3x3 Sobel operator. You know what I mean? 3x3, the resolution is 45. You can only specify 48 direction, which corresponds to 45 degrees. But in a very ideal condition, okay? The estimate accuracy can be up to 5 degrees. So that's why Sobel is so popular. And the other way, that's because all the filter value are integer, okay? So the calculation is pretty fast. But if you insist to use more accurate elements, here's another one called chain and free. Again, there's the author's name. In the early days, is square root 2, which corresponds to the true Euclidean distance. 它真正用 OGE 的距离。So in this case, it means the gradient will be the same for horizontal, vertical, and diagonal. If you go for the square root 2, okay? But the disadvantage for this filter is what? Because when you use square root 2, the value is not integer, okay? Computation time will be a little bit longer compared with Sobel operator, but that's another choice called chain and free. But we need to go back, but I already mentioned that if A, B, C, D, E, F is the graph value, and when you do the Sobel operation, that's how we calculate GX, GY. That's it. Okay. But anyway, you know what I'm saying. I mentioned about the convolution last week, right? So we need to carry out the convolution with the filter, right? For our case, for 3 by 3, that's the convolution, right? That's it. Okay, and you need to apply this for all pixel point xy. Then you carry out this operation, and W could be the pre-weight channel free or Sobel operator. Okay, the so-called convolution. And this is the basic operation in a convolutional neural network in deep learning. That's the basic operation. But the only difference is the filter here is determined automatically by your convolution, neural network. That's it, okay? But for our case, up to now, all the filters are predetermined, okay? They are predetermined. This is convolution. And you need to carry out this, okay? That's what I'm saying. If we use chain and free, okay, chain and free, that operator is square root 2, then this operation must be in real number, okay? The calculation must be in real number. But if we go for the Sobel operator, then all the calculation will be defined in integer. Because as I keep mentioning, the input image got to be integer. XY are integer. The square value are integer, even for color. We'll talk about that later on when we come to the deep learning model, okay? We'll talk about how you handle the color, okay? Or the so-called multi-channel input, okay? It does not have to be RGB, okay? It can be a 10 dimension or 100 dimension, it doesn't matter, okay? So that's how we do it with one-dimensional, okay? With with the first derivative, okay? Here, the last one for the edge detection filter. The other one, another name you need to remember is called Roberts operator. It's the smallest filter. It's only 2 by 2. Most of the Sobel operator or any pre-weight operator, any others, usually the operator got to be 3 by 3. But now when we come to the Roberts operator, it uses 2 by 2. The filter is only 2 by 2. The good thing about 2 by 2 is what? The calculation will be very fast compared with 3 by 3. Because 3 by 3 has 9 elements, right? 2 by 2, there's only 4 elements. But it's still based on the derivative, okay? So here's how it defined it, okay? It defined D plus D minus. This is the D plus. If this is XY, then you calculate the difference with respect to X plus 1 and Y plus 1. That's it, okay? X plus 1. If this is XY, now this X plus 1 and Y plus 1. Now it depends how you define it. It doesn't matter, okay? And the other one is X, Y plus 1. Here's X plus 1 and 1. So you calculate the difference for these two distances. That's it. If you remember when you learn the calculus, you will talk about you learn the derivative, right?
Yeah.
Then, have you ever remember or heard of called directional derivative? Directional 方向导数，有没有听过？ Why the derivative must be along x-axis? Why it must along y-axis? No, it can along any direction. That's so-called the directional derivative, right? 为什么只是跟顺着 x 轴做微分 ？Right, this along the horizontal line, the 0 degree. This is along the 90 degree. For this one, it's along 45 degree. We take the derivative along the 45 degree, and another derivative is 135 degree. Okay, so let's say it's still the first derivative, but with different directions. And in this case, it's only 2 by 2. So the good thing about it, the first is very fast. Second, you will get a very fine edges because it's small. You will have a very, very fine edges. 你说你那个边缘呢，看起来会更细腻。You can imagine if you don't believe me. If you have a edge detection 3 by 3, the other one will be 11 by 11. Then if you go for the 11 by 11, what would happen? For 3 by 3, you might have edges like this. For 11 by 11, this will be your edges. Because all the neighbors will have different response. So if you use a 2 by 2, then the edges will be very thin. But remember, some could be missing. But it will be very thick, very fine. Okay? 就是它会变得很细腻。你这个用的越大，它的 edge 呢就会越粗。Okay? So it depends on what is your purpose or what is your task. Okay, but anyway, remember they are fusing the first Sobel operator or go for the robbers. 2 by 2, that's it. Okay, that's it. Okay. Just the expression for the robbers operator, that's it. Okay. But at the end, it still need to, okay, take the absolute value, okay, in the 45 derivative and 135 derivative. You need to d plus and take the square or take the absolute value, okay, and d minus, and that's it. Okay. Okay, now let's talk about, maybe I should skip it, but let me just show you why you get the Laplacian. Okay, let me show you why you will get the Laplacian. Why you get the Laplacian here. The second derivative. Okay. Now, first we think of the first derivative using the so-called backward. Okay, we take the backward first derivative. X minus 1. That's so-called the first derivative. Okay, backward. It doesn't matter forward, backward, but you use it backward. Okay, I skip delta x. Okay, I'll put it here. That'll be fine. Delta. That's the first derivative. Okay, now, so this is the first derivative. Now, let's think of the second derivative. The second derivative is the first derivative of the first derivative. 不是吧？啊，一阶微分再一阶微分就是二阶微分。Now, this is backward, okay? We call this code backward. Now, we take the second derivative with the forward. We use the forward, okay? Now we use the forward. So, this is supposed to be what? F prime, because we use forward, should be right? Right. Square, because this is the first derivative. Okay? Okay. That's it. And now what is this? And what is this? This is because we are taking the first derivative. So the first term here is x plus 1 minus x, because we are taking the forward derivative. We are taking forward derivative. So this is f prime x plus 1. So this got to be. So we put x1 here. Now x becomes x plus 1. Everyone following? And this is x plus 1 minus 1. So it becomes x. 记了，因为我这边是 x 加1，所以我把 x 加1 replace this with x plus 1, and x is replace x plus 1, and minus 1 becomes x. So that's how you got here. Okay? And the second term, the same here, is this, okay? X. So we put x here, and x minus 1 here. That is exactly this term. So that's it. Okay? So this is for x. And then now we extend it to y. Okay? So dx can be written down like this. So eventually, then you will have 1 minus 2 and plus 1 here. Everyone follow me? Okay? So the same thing here, if you take the second derivative with respect to y, then that will be x, y plus 1 minus 2 f of x and plus x, and y minus 1. You take delta y or delta x to be 1. Okay? And remember, because we are talking about the magnitude, so we have to take sum them up, okay? The second derivative with respect to x, and also the second derivative with respect to y, which means you need to plus this term and plus this term. So in a total, what you get is if you plus them together, you can find. So x plus 1 y. Let me put it here. If this x, y, this x minus 1 y, x plus 1 y, it will be x, y, minus 1 x y plus 1. Now let's take a look x y. What is the coefficient for f of x y here? Minus 2 plus minus 2. See that? So it's minus 4. We need to sum them up, right? So this value will be 4. What about x minus 1 and 1? Here, this is x minus 1. It's 1. It's 1. It's 1. And it's 1. I should put minus 4. And this is 1, 1, 1, and 1. What are these? There's no coordinate for this point, right? So it means 0, 0, 0, 0, which corresponds to our Laplacian operator. Okay, that's why you call it Laplacian operator. It's based on the second derivative. 是这样来的 ，OK， 好吧，就这样。知道这些干嘛？就用。Try use the magnitude. Okay, basically for the second derivative, you need to look for the sign, but it will be too complicated. Okay, because you need to look for all possible direction and see if there's any sign changes. When I say sign changes, I mean from positive to negative or from negative to positive. Just look for the magnitude. Okay, just look for the magnitude. Otherwise, it's too complicated. But anyway, that's how we get Laplacian operator. Okay. Now, as I mentioned, you can extend it to. You put 8 here. Okay, and all the neighbors, 8 neighbors with the magnitude of 1. That's still okay. Okay, but anyway, that's how we get it. Okay, that's how we get it. Okay, so that's what I'm trying to say here. Okay, so it's called Laplacian. Okay, when you use OpenCV or any image processing software, you need to search for Laplacian. Okay, when you input the second derivative, you may not find anything. Okay, you need to type in Laplacian operator or edge detection or edge detector. Could be sometimes called edge detection, sometimes called edge detector. Okay, then you can find the corresponding function for your application. Okay. Here, give you the example here. Okay, suppose this is our image. Okay, we have on the left-hand side, we have the graph value of 4. On the right-hand side, we have the graph value of 8. So if we just take a look at the x horizontal profile, that will be, we have a curve or signal like this, right? It changes from 4 to 8. Now, if we apply this Laplacian operator, here's what you got here. You can get 0, 4, okay? So when you put the Laplacian filter right here, a 3 by 3, with this as the center, then you will return 0, right? Why is it 0? Because they are all the same, okay? Because we have a 4, 1, 2, 3, 4. And in the middle is 4 by 4, 16. And all other will be, you have a 4 value of 4, that was 60, okay? That will be the same, right? I put a cross here, it means don't care, okay? Don't care, because it is in the border of the image. But for this one, which means for this one, this is 0, when you put the filter with the center right here, so the difference will be 8 and 4, so the difference will plus 4. But when you move it to here, the difference will be minus 4. Okay, so you can see the sign changes here. So if it is the original signal, when you take the, after the Laplacian operation, see that? you will change the value from positive 4, positive, and then to negative. Okay? To 0 to 4, and 4 to minus 4. So I know this got to be an H point. Okay? But I still encourage you, not try to identify the direction of sign changes. It's too complicated. Okay? Just look for the magnitude. Okay, just look for the magnitude. That will be good enough. Okay, good enough. Okay, so this just give you the example. If you go for the second derivative, or you go for Laplacian operator. Okay. Okay. I also mark here Laplacian. This is a 3x3 Laplacian operator, or if you want to go for a 5x5 Laplacian, that will be 5x5. That will be the result here, because 5x5 is 25, right? You need to use up to 25. So in the middle, you put 24, and all other 24 elements have the value of 1. Okay, so that's it. Okay, so that's it. Okay. If you are not, I assume you are not just satisfied with everything offered by the OpenCV or any image processing tool. Here's something you can develop your own filter. Okay, you can develop your own filter other than the neural network. The first one that you can do is called, I don't know, OpenCV provide this function or not. Anyway, it's called derivative of Gaussian. So first, for a Gaussian filter, if you remember, if you have a Gaussian function, what is the purpose of Gaussian filter? If you have a Gaussian filter, if you use it, remember I mentioned you can use a Gaussian filter to design your own filter for image smoothing, right? Remember, the only thing you need to provide is what? Is the bandwidth, right? And the window size, and the window size. So a Gaussian filter itself is used for smoothing. And you know, to identify the edges, you need the first derivative, right? So why not we take the derivative of the g function. Now the derivative of g function then can be applied for edge detection and also for smoothing, which means you can use one single filter for two tasks, one for smoothing, one for edge detection, that's it, but with one single filter, which means you don't need to apply smoothing filter first and then go for Sobol operator or anything else. Now you just apply one. Okay, filter, the so-called derivative of Gaussian. Okay, so here we just take a look of the one-dimensional case. Okay, but it's the same as two-dimensional. Here's how we define a Gaussian filter, right? For the user, the only thing you need to determine is what? Is the bandwidth. The bandwidth. Okay? You need to determine what will be the filter you're going to use. Okay? A very sharp one or a very smooth one. You know, the larger the sigma, the larger the smooth effect, right? That's it. And then we take the derivative. We take the derivative. This is our Gaussian function g. What is the derivative of a Gaussian function or exponential function? the derivative of the exponential function is also an exponential distribution, right? 高斯函数的微分还是高斯 but we need to apply the chain rule. So the derivative of exponential distribution is still an exponential distribution. But if we take, so the G prime will be the G function itself. But we need to take the derivative of this term. So it's nothing but just 2x or something. We just drop the scale. It will becomes x times g. That's it. That's it. So it means what? If we want to identify the vertical line, see that? All the x are 0. So everything times 0 becomes 0. So the filter will look like this. Got to be 0, 0, 0. What about this? If this is minus 1 and minus 1, then you put minus 1 into this function. So you might get 1, 2, 1, for example. Okay, minus 1. So this can be applied for smoothing. At the same time, you can use this filter to identify the vertical direction. That's the purpose, okay, of derivative of Gaussian. When you extend it to two-dimensional, okay, as you know, two-dimensional Gaussian function can be separated into the multiplication of two one-dimensional Gaussian. Okay, 1 for x, 1 for 1. That's it. Okay, this is the final result here. So here. Okay. So this is the G. This is the GX. Okay, this is the GX. And this is, so I mean, you can use this, okay, derivative of Gaussian to design your own filter. That's what I'm trying to say, okay? You can specify the sigma, different sigma, then you can design your own filter, okay? Once you give the bandwidth, once you give the filter size, okay? So the following, this is the original image. Then on the right, we put a lot of noise in the original image. Then we apply a derivative of Gaussian, okay? With different mask size, which is the window size, and different sigma, okay, the bandwidth. And you can see the difference from here, okay? So if the window size is small, okay, and you can see fine edges, and somehow you can reduce more noise, okay, and with a large mask size, then you see that you can see a thick edges, right? Okay, so it depends on how are you going to use it. So whenever you try to apply the edge detection, in especially derivative of Gaussian, we need to determine what should be the best window size, what should be the best signal or bandwidth, so that you can effectively intensify the edges. At the meantime, you can reduce the noise, okay? You can reduce the noise, okay? So that's the example that you can try out, okay? For each row, it means you use the same window size, okay? For each column, it means you change the window size, but with the same sigma value, with the same bandwidth, okay? So you can compare the difference, okay? Row by row, or by column, okay? And you can see what will be the difference, especially from the very first one. Okay, you can see a very fine edges with more noises. To the last one, you can see you can reduce the noise a lot, but you will see a very much more thick, okay, edges. That's something you can expect, right? Okay, so that's it. Okay. And the other one is called Laplacian of Gaussian, okay, LOG, okay, LOG. The original one, when you read the paper, and I don't know if the OpenCV provide this, is sometimes it's called DOG. It's called DOG, okay, DOG, DOG, okay. Derivative of Gaussian, okay, DOG, the derivative of Gaussian. It's based on the first derivative, or you can apply LOG, okay, LOG, called Laplacian of Gaussian. Laplacian is based on the second derivative, which means if you have a Gaussian distribution, then you can calculate the first derivative, right? And then, of course, you can calculate its second derivative. So you can use it to remove noise and also identify the edges based on the second derivative. Okay, I will skip the details more because most of the time you might use the DOG, but we hardly use LOG. But anyway. I will skip the details, okay, because it's just based on the second derivative, okay? The first derivative and take another derivative. And a Gaussian derivative is also a Gaussian. And the derivative of Gaussian is still a Gaussian. Anyway, the final result is like, this is the final result here, okay? The final one here, take a look. You still see a Gaussian distribution, okay? And the first term here is a constant. We can drop it. It's a constant. The only difference is right here. See that? It says 1 minus and times Gaussian, okay? And the previous is nothing but a constant. We can drop the constant, okay? And this is still a Gaussian distribution. So the only difference is right here. Now take a look. Here. This is what? This is, or if you want, I can put it. See that? So it's what? This is a circle. This is a circle. So we use this term to define the positive. We design a filter if everything is less than 2 sigma square, then the value will be positive. See that? And everything outside the filter outside the circle will be negative. Just like four. See that? See that? Everything inside the circle is positive. Everything outside the circle will be negative. That's the idea, okay? For the LOG, Laplacian of Gauss, okay? So the sigma will determine what should be the size, and what will be the positive, what will be the negative value. Okay? And again, G function is used for smoothing, right? And this is used to identify the edges. That's it. Okay? But it's just for you to have some more knowledge on the background, or you want to develop your own filter. If you just care to use the OpenCV, the only thing you need to remember is just to use Sobo or Roberts, or 3x3 or 2x2. That'll be good enough. You don't need to. But for some very specific application, you might need to design your own filter or something. Or if the image processing software provide DOG or LOG, then you can specify your own, okay, your own applications, or design your own filter for your very own purpose. Okay, so that's all. Okay, we still just a few minutes, but I will stop here today. Okay, the last thing, I don't have the time to talk about it. Next week, I will talk about the so-called Kenny edge detector. Okay, it's a very, very important technique for edge detection. Very famous one. Okay, very famous one. Still edge detector. But let me show you, because it's still a couple of minutes, let me just show you the result, okay? You need to run this so that you will know how to specify the parameters when you apply the Kenny edge detection, okay? But here's the result. This is original image. Actually, it's wafer ingot. 那个细晶锭，就是晶圆切割前的那个晶锭。Okay, in a magnified in a microscope. This in the middle is based on the Sobo operator, 3x3 Sobo operator. This is based on the Kenny detection. See that? I mean, when you go through the Kenny detection, the edges almost is 1 pixel width. 它的宽度会变成大概只有1个 pixel. Okay? Next picture will be more significant. Okay, this is a PCB. You know, it's a PCB, printed circuit board. Okay, this is Sobo operator. Okay, it looks nothing wrong. Okay, that's great. But when you take a look about the Kenny detection, I mean, the edges is very thin, almost 1 pixel width. But what is the disadvantage? Take a look. What's wrong with Kenny? That's something when you apply it, you must keep in mind. The edges are broken. See that? See that? Some of the edges, they are broken here. Okay, see that? They are broken. Okay, it's not fully connected. That's something you must keep in mind when you apply it for your own application. Okay, you must ask yourself, will it be okay if I have something like this? Or you do have something like this, what can you do? Okay, what should be the process to make sure they are all connected? Okay, otherwise you may go some other way. But anyway, the good thing about candy edge detection especially when you talk about Hopf transform, we prefer to work on the candy edge instead of that because there are too many edges. It's too thick. It's not fine enough. Okay, so anyway, the good thing is about it, you will have a fine edges, but it's not fully continuous. Okay, that's something we must keep in mind. So next week I will talk about how to do the candy edge detection. You are not going to write your own candy edge detection, but you got to know what are the parameters. There are quite a few different parameters for candy. Then you know how to make a judgment so that you will fit your own application, okay, and for your task. And after that, I will talk about corner detection and Hopf transform, and finally, I'll talk about texture analysis in a traditional way, how to extract. I just keep saying how to distinguish the difference, right, of the white wall or the white ceiling. It is a lot of situation, and hopefully I can finish in no more than 3 weeks. Hopefully I can finish in 2 weeks, and because for deep learning we still a lot of different topics to talk about. Okay. I'm a kind of rush, but anyway, I just try to show you everything you need to know in computer vision. That's my only purpose for that. Okay, so far for today, but we will continue our class next week. Okay, no written exam. Okay, thank you, and see you next week. 这个你要